With the rapid economic development and information technology revolution in India, the demand for reliable quality power is growing steadily. Over the past 30 years, the demand for energy has grown at an average of 3.6% per year. India is the world's sixth largest energy consumer, accounting for a little over 3% of the global energy consumption. Karnataka, as a state, has a long history of using renewable sources of power. In Karnataka, renewable energy accounts for 20.1% of the total energy consumption. This is well above the national average of 7.7%. Coal is a solid fuel with very high carbon content. Carbon is a chemical element which burns in oxygen to release large amounts of heat. This is the heat that is converted into electricity at thermal power plants. Almost 90% of the coal mined around the world is used to generate electricity. Thermal power plants use coal to heat water into steam. This steam is built up to very high pressure and then used to turn turbines. The spinning turbines drive huge generators and thus produce electricity. These turbines turn in a magnetic field and, according to Faraday's law, the changing magnetic field that each turbine sees generates an electric current. This electric current is then stepped up or down to the required voltage by transformers at the power station and at home. Here at the museum, let's take a look at how power is generated at a coal-fired thermal power station. First, the coal is crushed and then blown into the boiler to burn. In the boiler furnace, coal is burned to produce heat. The heat from combustion of the coal boils water in the boiler to produce steam. The steam is then piped to a turbine. The high-pressure steam impinges and expands across a number of sets of blades in the turbine. The impulse and the thrust created rotate the turbine. The rotation of the turbine rotates the generator rotor to produce electricity. The steam is then condensed and pumped back into the boiler to repeat the cycle. Electric energy thus produced is led through a system of transformers and distribution grid to reach the consumers. Unfortunately, thermal power plants run into two huge disadvantages in the long run. Despite the fact that they are inexpensive compared to other power plants, the scarcity of fossil fuels presents a major problem. The second and more worrying problem is that of pollution. When carbon or any fossil fuel burns in air, it produces a whole host of poisonous and toxic gases. The primary product is carbon dioxide, a gas with a peculiar and harmful property. Carbon dioxide, written chemically as CO2, consists of one carbon atom bonded to two oxygen atoms. It is a gas. Because of the carbon dioxide concentration in the lower atmosphere near the surface, some of the re-emitted infrared rays are directed towards the surface, which heats it. This is the greenhouse effect. This effect is actually a necessary effect for life on Earth, but in moderation. Due to uncontrolled emissions of carbon dioxide, the warming effect of carbon dioxide is slowly leading to a rise in the average temperature of the Earth, a process known as global warming. It is not only thermal power stations, but also petrol and diesel-powered vehicles that contribute to the increase in greenhouse gases. The rise in its amounts around the world is cause for concern and the reason for the search for clean and renewable sources of energy.
So now we have to come up with sources of energy that overcome the disadvantages of fossil fuels. Fortunately for us, there are plenty of choices. Wind power is one of them. Wind energy is used to turn turbines in much the same way that steam heated by coal turns turbines in thermal power stations. The source of energy for wind power is ultimately the sun. How is that? For a quick explanation, let's step into the weather studio. Infrared rays from the sun tend to heat up the Earth's surface much faster than they heat up water. This creates an area of low pressure over land and an area of high pressure over water. This causes the air molecules to tend to move from the water to the land, creating a wind. If you place turbines to intercept this wind, that is what is generating electricity in wind turbine power plants.
The electricity produced is then supplied to the existing grid system for distribution. Generally, wind turbines are designed to operate at wind speeds between 15 meters per second, that is 54 kilometers per hour, and 20 meters per second, which is 72 kilometers per hour. The blades rotate at 10 to 22 revolutions per minute. Generation does increase with increase in wind speed, but a safety mechanism shuts off the turbine if the wind speed increases to 20 meters per second. Wind power is not a new idea. Human beings have used wind to power ships, to help with irrigation pumping in farms, and of course to grind grains in windmills. However, their use as sources of electricity began only in the later 19th century. Wind power is currently the second most widely spread source of renewable energy behind hydroelectric power.
Hydroelectric power plants are the biggest and most widely spread source of renewable energy in the world, accounting for 15% of the world's electricity. Here at the museum, the working of a hydroelectric power plant is clearly explained in this interactive display. The driving force for the turbines is gravitational potential energy. Just like in a dam, the water that's stored in this tank also has potential energy. When it flows down the pipe, it turns turbines, which generate electrical energy, exactly like in a hydroelectric power plant. This energy is converted to electrical energy. The force of moving water is very powerful, and a hydroelectric plant uses that force to generate electricity. Hydroelectric plants are built near moving water, such as rivers, and also at man-made facilities such as dams that create moving water. The potential energy of the falling water is converted to mechanical energy as the force of the water turns the turbine. The generator connected to the turbine rotates, converting the mechanical energy into electrical energy. Hydroelectric power is economical. It helps conserve our fossil fuels and is clean and an environmentally friendly source of energy.
As we saw with the thermal power plant, if we generate lots of steam, then we can use it to turn turbines. So, instead of using fossil fuels, we could use other organic fuels like wood, alcohol, or plant matter. This is what happens in a biomass plant. The plant matter is burnt to produce heat, which converts water into steam. This steam turns turbines just like in a thermal power plant, and electricity is generated. Geothermal power plants work on a similar principle, except in this case, we harvest the natural heat present beneath the Earth's surface. This is the same heat source that produce natural geysers. So, geothermal power plants have to be built in very specific locations, as we can see in this display. The steam that is naturally generated well below the surface is brought up to the plant to turn turbines. The steam condenses and is returned to the earth as liquid water, which may get heated up again and re-enter the cycle.
Nuclear power plants work on a principle discovered by Einstein and encoded in the most famous formula in science, E equals mc squared. According to this equation, matter is just a very highly concentrated form of energy. So if we could find some way to convert matter into energy, our energy problems would be solved, because the conversion factor is the square of the speed of light, which is an unimaginably huge number. Unfortunately, this is easier said than done. The only way that this has ever safely been achieved is in the fission of uranium atoms. Uranium is very heavy compared to other atoms. Its nucleus contains many protons and neutrons. When a neutron hits a uranium nucleus, it causes the nucleus to split. When the uranium nucleus splits, it forms two smaller nuclei. Each of these nuclei releases one neutron. What is interesting is that if we add up the weights of the two nuclei formed plus the two neutrons released, it is always less than the weight of the original uranium nuclei. What has happened to this excess mass? Well, Einstein told us that mass and energy are effectively the same thing. So this mass was lost in the reaction and converted entirely to energy, according to E equals mc squared. Now, one uranium nucleus splitting is not going to produce any significant amount of energy. But remember, the breakup of the nucleus also released two neutrons. These neutrons could travel further and hit two new uranium nuclei, release energy, and produce four neutrons, which could do the same thing again and again, producing what's known as a chain reaction. Every time a neutron splits a uranium nucleus, a small amount of energy is released. But since the reaction, once initiated, produces its own neutrons, the amount of energy that can be released is huge. The nuclear fission generates a lot of heat energy. This heat energy is used to heat water to a very high temperature and turn it into superheated steam. That steam is represented here in this model by flashing red lights. The steam then travels through pipes until it reaches a generator, where it is used to turn turbines to generate electricity. Once the electricity is generated, it can then be transmitted using a transformer. Nuclear energy has its pros and cons. Its use as a source of energy is the cause of much debate. We saw in Japan, after a tsunami hit, that the nuclear reactor at Fukushima had a meltdown and leaked radioactive materials.
Explosion occurred in the number 3 reactor building of the Fukushima number 1 nuclear power plant at around 11 a.m. Japan time on Monday. It was likely triggered when a combination of hydrogen and oxygen was ignited. The wall of the building has collapsed, but Chief Cabinet Secretary Yukio Edano briefed in the press conference that there is low possibility of mass radiation has leaked, and he is right now collecting data of radiation.
On the other hand, nuclear power does not release greenhouse gases, and it produces cheap energy. So what do you think of the whole debate? Well, you can register your opinion here at the museum and see how many people you have on your side. Is it a magic lamp or a ticking time bomb? It is no surprise that early religions worshipped the sun. Solar power is hailed as the solution to energy problems worldwide. Since most of the energy on Earth is anyway indirectly a product of solar energy, it is only fitting that eventually direct use of solar energy would be a solution to our energy problems. There are basically two ways in which solar power can be used to generate useful energy. The first way is by using heat from the sun to generate heat on the surface of the Earth. Depending on the amount of heat collected by the solar panels, the energy can be used to heat water or, if in large enough quantities, even produce electricity. The second way is to use light from the sun to power a photovoltaic cell. Photovoltaic cells, or solar panels, convert sunlight into electricity. A solar power system consists of a solar panel, a battery, and a charge controller. Solar panels produce direct current, or DC. When a solar panel is connected to a battery, this power is stored in the battery for later use. A charge controller connected between the solar panel and the battery monitors the battery and prevents the solar panel from overcharging it while assuring a complete charge. A solar-powered system requires an inverter when the DC power needs to be converted into an alternating current. The efficiency and convenience of solar panels is the focus of this display at the museum. Daylight is simulated using a light bulb. During the day, solar panels collect energy which is stored in batteries. Then, when night falls, this stored energy is used to power street lights and homes. Depending on the intensity of the sunlight it is exposed to, it can generate different amounts of electricity, enough to power your cell phone or even a car. Let's see how. The solar car is an electric vehicle powered by solar energy obtained from solar panels fixed to its roof. Right now, solar cars are not a practical mode of transportation, but are primarily demonstration vehicles. There is an inexpensive way to demonstrate how solar power is generated. The current produced in this cell is very small, but it is still detectable. We begin with a copper plate. It is heated on an electric stove until it develops a layer of red cuprous oxide, followed by a formation of a layer of black cupric oxide. This is allowed to cook for about half an hour and then cool down. Okay, so I think our copper is cooked enough for now. Now, as I turn the stove off, the plate will cool, and as it cools, the black cupric oxide layer will begin to flake off. So as we see, our plate has started to cool and the cupric oxide has started to flake off. Now we just need to wait for it to cool completely and then scrub off the cupric oxide layer. Okay, now our copper plate is ready for the experiment. The cupric oxide layer is flaked off and in fact it's now cool enough to hold. We also need an electrolyte to complete the circuit. We just use salt in water. Salt water is an excellent conductor of electricity. We then take our cuprous oxide plate and place it in the electrolyte and connect it to the positive end of a microammeter. We connect the negative end to a fresh copper plate and place that in the electrolyte, thus completing the circuit. we now have a solar panel. How can we tell? In ordinary light, if we switch on our microammeter, we see that the reading is around 52 microamps. But if we bring in another light source, like a light bulb, imagining the light bulb to act like the sun, we see that the microammeter reading goes up to almost 70. If all the lights were suddenly to go off, in near complete darkness, the microammeter reading drops drastically to around 31 microamperes. But then if we move our sun in front of the cuprous oxide plate, we see the reading goes back up to almost 60 microamps. And then once again switching on all the lights, the reading goes up further to about 65 microamp. The current intensity in the circuit clearly depends on the intensity of light. This is how light energy is converted to current in a photovoltaic cell.
A fuel cell is a device that converts the chemical energy from a fuel into electricity through a chemical reaction with oxygen or another oxidizing agent. Hydrogen is the most common fuel, but hydrocarbons such as natural gas and alcohols like methanol are sometimes used. Fuel cells are different from batteries. They require a constant source of fuel and oxygen to run, but they can produce electricity continuously as long inputs are supplied. The first commercial use of fuel cells was in NASA space programs to generate power for probes, satellites, and space capsules.
So far so good, we've generated lots of electricity. But how does one get it from the power plant into our homes?
Electric power is normally generated at 11 kV to 25 kV in a power station. To transmit electricity over vast distances, it is then stepped up to 400 kV or 220 kV or 132 kV as necessary. Power is carried through a transmission network of high voltage lines. Usually, these lines run into hundreds of kilometers and deliver the power into a common power pool called the grid. The grid is connected to load centers in cities through a sub-transmission network of normally 33 kV or sometimes 66 kV lines. These lines terminate into a 33 kV or 66 kV substation where the voltage is stepped down to 11 kV for power distribution to load points through a distribution network of lines at 11 kV and lower. A transformer further reduces the voltage from 11 kV to 415 volt to provide the last mile connection through 415 volt feeders, also called as low tension feeders, to individual customers, either at 240 volts as single phase supply or at 415 volts as three-phase supply. This is then available to us to use as we see fit.
The future of humanity depends on our ability to find renewable and clean sources of energy. The days of carbon-containing fuels being burned are numbered. The Vishveshwaraya Museum has a number of displays dedicated to renewable sources of power. Let's take a short walk around and see what we find.